Hi, I'm Mitch Luman, Director of Science Experiences here at the Evansville Museum. And today we're going to do some pretty cool experiments using a material that's fairly common, but fairly unknown. It's nitrogen. Now, this room is filled with air, and the air has lots of different materials in it. But before we start talking about gases, we need to talk about the other two states of matter. Do you know what the three states of matter are? Well, here's one. This is a block of rock. This is a solid. You know what the other states of matter are? This beaker contains liquid water. Liquid is another state of matter. And you know what the third state of matter is? Well, it's the gases in this room, as an example, or in this container, in this case propane, which is used to create flames. These three states of matter are basic in our universe. There's actually a fourth one called plasma, but we won't get into that today. Can you think of a material that exists as a solid, a liquid, and a gas? Well, maybe not, but water is a great example. For instance, when water is frozen, it exists as a solid. When water is warmer than being frozen, it's a liquid. And when it's much warmer than a liquid, it changes into a gas. And some materials can change from gases to liquids to solids. Just depends on the temperature. Before we talk about temperature, and before we talk more about this amazing material, nitrogen, we need to talk a little bit about molecules. You and I and everything are made up of atoms, and those atoms are stitched together into molecules. Here's an example of that molecule that I talked about earlier, water. It's H2O, two hydrogens and one oxygen atom. When you put those two hydrogen atoms together with an oxygen atom, you get water. It's a great example of a molecule. Nitrogen is a molecule as well, and it generally exists in the air as N2, which means nitrogen, nitrogen, or two atoms of nitrogen connected together. And then that brings us to temperature. Temperature is a function of how fast those molecules are moving. Let's step back for just a second. This room is filled with molecules, and they're vibrating. They're very tiny. You can't see them. Depending on how fast a molecule is vibrating, it could be hot, it could be cool, or it could be really cold. When molecules vibrate very slowly, thermometers show that as a cool temperature. When molecules vibrate faster, it's room temperature. And when molecules vibrate extremely fast, keeping in mind you can't see this vibration, thermometers register that temperature as very hot. I have a way to demonstrate that. I'm going to remove my personal protective equipment for just a moment, and we're going to talk about the science of cold. This is a adding machine tape with some numbers on it, and we're going to start off by looking at the temperature in this room. And we're going to see how cold we can go and where it would fall on a scale. This is room temperature, 70 degrees. It's not freezing, not too hot, not too cold, but what's colder than 70 degrees? Well, 32 degrees. Tens of degrees colder, this is freezing. This is where water would turn into a solid. Nitrogen, which is a gas, exists as a gas at room temperature and also at freezing. You cannot change nitrogen like water into a solid at 32 degrees Fahrenheit. How cold must one go? It does turn into a liquid, but not at this temperature. It's much too warm. Let's continue on the roll of paper. How about 0? That's 70 degrees colder than room temperature. Does water freeze at 0? Of course, it's already frozen at 32 degrees. It just gets even harder. But nitrogen gas and many other materials, they don't even turn to a solid, not even close at that temperature. So again, how low do you have to go? You could go to minus 100. That is 100 degrees colder, 170 degrees in fact, colder than room temperature, but still, nitrogen does not turn into a liquid. It's still a gas. How about minus 200? Nope. Lower? How about minus 300? That's pretty cold. That's about as cold as you can get in the universe, but you can still get colder. A whopping 321 degrees. That's how cold one must take a gas known as nitrogen before it turns into a liquid. I'm going to put on my personal protective gear now, and I'm going to show you what this material looks like. It, again, exists as a gas in the room. In fact, the room is filled with this gas. There is 78% of the air, everywhere you go on Earth, is made up of nitrogen gas. Let's just do a little experiment before I introduce you to this amazing material. Everyone take a breath. A really deep breath, and let it out. You just inhaled and exhaled. Your body took the oxygen in the air and used it for your life functions. Your body has no use for nitrogen, so the nitrogen was expelled with every breath you take. It's an inert gas, but it is very, very common, and with every breath you take, you suck in mainly nitrogen gas. Fortunately, there's enough oxygen in the air to sustain your life. In order to transport this material, nitrogen, as a liquid, you need a special vessel. And this is known as a Dewar Flask, and it's a specially insulated thermal glass container that keeps this material as a liquid. If it weren't in this container, the material would vanish, and I'll show you why. As a liquid, nitrogen is a clear, colorless, but very cold liquid. And as it's introduced into the air, it disappears pretty much instantly. Now, you'll probably see some condensation here at the lip of the container, and that's not nitrogen gas. That is actually super cold air in the room turning into a cloud. It's a fog, more or less. So this colorless, very cold liquid actually is boiling at room temperature. What else boils? Well, water does, and I'm going to make a demonstration here which shows you that this material that we're experimenting with today does boil at room temperature. If you were to put water in this kettle, what temperature would be required to cause it to go from a liquid to a gas? It's about 212 degrees Fahrenheit. Liquid nitrogen boils at room temperature. So let's put a little bit of this material in this tea kettle, and let's listen and see what happens. Ready? Did you hear that? What you heard was the nitrogen expanding in this container and turning into a gas. The whistle is the same whistle that you'd hear if there were water in here and it was hundreds of degrees above room temperature. Liquid nitrogen changes pretty much instantly into a gas, causing it to cause the same whistle that you would hear if water were boiling. There are a few other containers that you can use that can contain this material, and I have another one right here, and this is another very insulated material. If it were not very thick and very heat-proof, the material in here would evaporate. I want you to notice that I have in my hands a balloon, and there's an opening here that is not exactly large enough to hold the balloon. But let's see if I could somehow stuff this balloon into this container. Nope, doesn't work. The balloon is much too big to get in there, at least right now. But what would happen if I were to chill the air inside of the balloon using this super cold material inside? Let's see. Somehow I managed to get the balloon inside, and I'm going to put it a little further inside using these forceps. So the first thing you want to notice is that the balloon wouldn't fit before, but somehow it's fitting inside the container right now. Let's get the balloon out of there and see what's happening. Well, you probably have noticed what I've noticed. The balloon has shrunk, but there's more. As the balloon warms up, the air that was previously very, very shrunken inside the balloon is expanding. How much will it expand? Well, it should expand to be the original size of the balloon because no more air came in and no more air came out. All I did was cause the air inside of this inflated balloon to shrink. Cold air takes up less space than hot air, or room temperature air in this case, and I was able to shrink the air inside the balloon so that it didn't push out as hard on the exterior of the balloon, and it shrunk to a very tiny size. Again, it still doesn't fit in there, but you could get it to fit again if I was to shove this down in there and cause the air inside the balloon to shrink once again. And you can keep doing this back and forth as long as you want. There's no opening in here causing the air to come in and go out. It's simply the fact that cold air takes up less space than warm air. Now, living things should not be subjected to these very cold temperatures. I have here a formerly living thing, a carnation, and it represents an organic material. It's mainly water. Let's see what happens when I make this carnation as cold as I can get it. I've immersed the carnation inside the very cold, minus 321 degree liquid material. As I chill the balloon, you might wonder what uses this material has other than cool science experiments. It's used in some medical procedures where things have to be very cold and then scraped off. It's also used in industrial processes and in making freeze-dried food, of all things, something I enjoy. Ready to see what the balloon looks like? Well, it doesn't look too different, but it is very cold. But the properties of the carnation have changed, I assure you, because watch what happens when I squeeze it. It pretty much shatters. So one of the reasons you would not want to get organic or living things really cold has to do with the damage that occurs when things not normally that cold reach temperatures where they should never be. Well, I hope you enjoyed this demonstration. This has been a presentation of the Evansville Museum. Thank you for watching.